part is composed by dark matter, about 10% from intercluster medium, which means the hot gas, hot plasma, and just 2% is composed of their composition is given by galaxies, okay? So I would like to emphasize it here because when we talk about richness, when we are trying to obtain a mass estimation using richness, we are dealing just with the 2% of these objects, okay? And as most of you, I think, know, when we describe the cluster mass by the X-ray signal, we are mostly talking about this intercluster medium, okay, and also SZ. And weak lensing, it's a new probe in this field, and it's a probe that we deal mostly with the dark matter, so it's very promising, okay? Here, contrary of Tom's presentation, I have a few equations and not so much graphics. So I hope the complementarity will begin like this. So we have the halo number density, okay? The number of galaxy clusters as a function of redshift and mass. And this is given by this depends on the area survey, the area of your survey. Here, the cosmological dependency on these quantities appears here on the Hubble function. This is the co-moving distance, okay? And this is the halo mass function, right? This is the mass density of the universe. This is here I'm going to call the halo mass. I put here galaxy cluster cosmology, but as it comes from theory, we are talking about dark matter halos, okay? So this is the mass of the halo. Sigma is the standard deviation of the density contrast. So it depends cosmologically, it depends on the Hubble function and also the linear power spectrum, okay? And this F here is what I call, and some people in the literature, the multiplicity function. So when we talk about the nonlinear regime, Tinker mass function, because some people use halo mass function to describe both this expression and also this F. But I would like to separate to talk about the uncertainties as Tom mentioned in his presentation. So just to illustrate, this is the number of galaxy clusters as a function of redshift, okay? So, and here we have this function for 3 different values of the equation of state, dark energy equation of state, okay? So this is galaxy clusters is a high sensitive probe to cosmological parameters, including dark energy. But as we see, we have to deal with some uncertainties to compute this quantity. So the first uncertainty source that I mentioned is the multiplicity function, which is related with the nonlinear regime of halo or cluster formation. Today we obtain fitting functions from any-body simulations, okay? And these, the results from the simulations depends on the halo mass definition, as Tom described earlier. And we have that Tinker multiplicity function. We have a 5% precision at redshift 0. And the recent result from Tom, he obtains 1% precision, which is required in LSST era. Okay, so this is the first uncertainty source that I mentioned. Then we have this. Usually people don't care too much about the second source here, which is the bias, the possible bias that your cosmological parameter estimators can have. So this is something that I I published in 2014, but I always like to remember when I have this opportunity that something that we have to take care, okay? Because usually we perform some analysis when you assumed, you build your likelihood and perform your statistical analysis, but usually people don't check if the estimators that you obtain, if they are biased or not. So usually people build a maximum likelihood, obtain estimators from a maximum likelihood procedure, but these estimators are not necessarily unbiased, okay, even if they are consistent, okay? So I think it's important to take care of it and perform Monte Carlo analysis and check if in your situation your estimators are biased or not. Depending on the case, this can be completely relevant for your analysis. So in this work, we studied different cases varying the maximum redshift survey area, including or not photometric uncertainty to obtain the redshift, and also the uncertainty on mass, okay? So we studied this typically for SZ surveys, in particular at the time for SPT, the South Pole Telescope. And we found that, for example, if we had a perfect scenario where you know perfectly the halo mass and also the redshift, we can obtain biases of almost 80% of the size of the respective error bar. So both on the density of the coded dark matter, this omega C, on sigma 8, and also on the dark energy equation of state. Okay, so including this uncertainty on mass and so on, we also obtain about 50% of the respective error bar, including the mass, the uncertainty on the mass. Okay, and when we join both photo Z and the uncertainty on mass, this bias drops a lot, and it remains just a few percent, a bias of few percent of the size of the respective error bar, okay? But this is something that we have to take care. And the good news is when we perform a joint analysis, in this case, we combined the cluster likelihood with CMB, the bias disappear, and we obtained unbiased estimators, okay? So next, we have another source of uncertainty. We have photometric redshift. Usually people model these uncertainty include in the analysis giving this Gaussian distribution of obtaining this photometric redshift given the true one, okay? And then we have to take to include the bias that you probably have, and the sigma, the standard deviation, which is described as a function of redshift and described like this. So here we have some numbers from large surveys, such as the dark energy survey, which performed the measurements using 5 filters, okay? And the sigma is of order 0.03. This for galaxy clusters, okay? This is higher for galaxies. The JPass, which is an ongoing survey, the measurements, they use 56 filters. So these standard deviation, they decrease for another smaller than DES, and this will be really nice to combine and to compare with the other surveys. The Euclid satellites, they will use 7 filters, and they expect this standard deviation, and they expect to measure galaxy clusters up to 2, redshift 2. And LSST, which will use 6 filters, and they expect this standard deviation for the photometric redshift, remember that you have to multiply by this factor and a small bias like this, okay? And we expect to observe a galaxy cluster up to redshift 1.2, okay? And the last one that I'm going to talk about is the uncertainty on the cluster mass. Today, this is the main source of uncertainty.
So, Mariana, sorry, if I'm not mistaken, I think JPass can only see clusters up to redshift 0.7.
0.7?
0.7, not 1.5.
Ah, okay. I have to...
Up to 0.7.
Okay. But this is to have a complete catalog, or... Okay. 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 Oh, because originally when I picked some documents, I got this number. So, okay. Thank you. So the main source of uncertainty for cluster cosmology today is the uncertainty on the cluster mass estimates, okay? The first huge problem is that mass is not directly observed. So you can observe some galaxies that compose this cluster, and with this you have the richness, and you can estimate mass from this observable, or you have the Compton factor if you are looking at SZ Sunaev-Zeldovich data catalogs or X-ray. So you have different observables from which you can estimate the mass, okay? Some of these observables give you mass proxies, such as those from X-ray or SZ, or even richness, okay? And in the end, when you build your likelihood, for example, this is the term, one term for the unbinded cluster count. If you consider just cluster abundance mainly for massive cluster, your likelihood will be the product over all clusters of this function. So you have this, an integral over the true mass, an integral over the true richness, okay? And you have to include, this is the theory, the number density, the number of clusters per redshift and mass. This is the probability distribution of observing richness given a true one. This probability distribution relates the true richness with the halo mass, and this is the probability the photometric redshift probability distribution. This fifth function here is the selection function, so it deals with the purity and completeness of your catalog. Okay. So you have given your data, you have a mass prox. Some observable that you are going to relate with the cluster mass, okay? And you have to forecast, people have obtained some forecasts, and they verified that you have to calibrate the max proxies within to 5% level over both mass and redshift, such that you can access the powerfulness that a galaxy cluster can give you to obtain cosmological constraints. Okay. In this sense, Weaklings is the most promising one because this observable is not sensitive to the gas astrophysics, differently from X-ray or even SZ. But to obtain individual cluster mass estimates from Weaklings, you can obtain estimates almost unbiased, but they are very noisy. Okay, so you have to play and deal with it. So that's why it's really important to use multi-wavelength analysis, combining both, for example, X-ray and Weaklings measurements, such that you can bring the best of these two worlds, okay, and trying to obtain a better mass estimate. Okay. So in general, you can find in the literature that people write a relation like this, relating the mass estimates given observable and the true mass, and here we are going to refer to this as the halo mass, okay? Modeling like this, as A is the slope, M0 is a pivot mass, and BO is the bias of this relation. So for cluster cosmology, one thing is that you are able to constrain both cosmology and calibrate your mass observable relation simultaneously. So this is what we call self-calibration, okay? And in this sense, it's really nice to perform some multi-wavelength analysis, okay? One thing here is that when we talk about X-ray, we usually have massive clusters. You can reach higher redshifts mainly for SZ also. And you can combine it from other clusters that you obtain from optical surveys, okay? But statistically, you have much more objects in optical surveys than the other ones. But even though it's really important to carry out some analysis, even if you have a few clusters, small samples, it's really important to perform this kind of analysis, trying to join both cosmology and self-calibration, and not because people usually focus on large samples and big catalogs, because you can think that it's just from this that we are going to obtain good cosmological constraints. But in the end, we want to understand both cluster astrophysics and cosmology. And this is a great tool to perform both, to study both of them, okay? So in the literature, people usually try to calibrate one relation, for example, SZ relations, given weak lensing mass estimates. But from this, using this formula, usually people assume that weak lensing masses are unbiased, so B is 0, and also they put that the slope, the SZ and the Sunyaev-Zeldovich and weak lensing slopes are equal to 1. And with this, they try to obtain the SZ bias, okay? So we note that usually performing this kind of analysis, you obtain underestimated error bars on BSZ. And this was really emphasized with the 2013 results from Planck, where they have SZ cluster mass estimates and perform cluster cosmology analysis, and they obtained some tension between the CMB and cluster results. So many people try to understand this, taking a look at the mass estimates and trying to obtain, using a follow-up with weak length mass estimates, trying to understand if the problem could be bias on the SZ mass estimates that they were not taking care, okay? So we note that this methodology was too simple and could underestimate the error bars, and this is due mainly to the strong assumptions that they were doing on the other parameters, right? So to do this, we introduced a new methodology to calibrate the mass observable relations that we called pseudo cluster counts, because normally you have the cluster counts likelihood to perform self-calibration or just galaxy cluster cosmology, and we introduced this likelihood where where we build like this, the likelihood is the product over the clusters you have in your sample divided by this normal, which is the total number of clusters you have, and you integrate over the true mass. The halo mass function is the density. Halo density is a function of mass and redshift, and this is the probability distribution. And specifically in the analysis we carry out, we use plank data and clash data. So this distribution corresponds to this integral of the SZ mass, the lensing mass, okay? This is not just weak lensing because the lensing mass estimates that they obtained combine both strong lensing and weak lensing information, okay? So this is the probability distribution. This is the probability distribution combining both this bivariate Gaussian distribution assuming this relation, okay? But with it, we didn't include any prior on B nor A, okay? Both for lensing and SZ information. And this is the probability distribution relating the true halo mass and the SZ and lensing mass, okay? So here are our data, okay, for SZ and for lensing. So we obtain these results for the SZ bias, okay, this is our results, and we compare with other results from literature. Our sample, we use just 21 clusters. Oh, and one important thing, why pseudo cluster counts and not use directly cluster counts likelihood is because we don't have the selection function. So this is another thing that we fit, okay? We fit all the parameters that we include for the relating the lensing and SZ masses, the observed and the true one, okay? And we also fit the selection function, okay? So this is another encouraging thing. Because, many times you can say, okay, I have some cluster mass estimates, I have a catalog, and for LSST, for example, you expect that massive clusters you obtain of order of 1,000 of clusters. So you have already a catalog big enough to obtain considerable constraints, okay? And you can stop your work and think that, okay, I don't have a complete or poor catalog, so I cannot use it. So this is another thing that we are excited about this methodology. Okay, so try to fit your selection function. Use this methodology and do physics, study the astrophysics, the cosmology, and also the selection function using this methodology and using all data you can, okay? So, okay, specifically we reduce the tension here from between CMB and clusters to this point, and that's it. Okay. So now I'm going to specifically talk about the weak lensing cluster mass estimate. Okay, the requirements that we need are the estimates of the distortion of each galaxy image due to the cluster shear. Okay, this is the shear. We need estimates of the redshift of all these galaxies because all quantities that we are going to compute, the tangential shear, the convergence, and the reduced shear, they depends on the cosmological distance between observer lensing, observer source, and the distance between source and lens, okay? So we need the redshift of each object, and also we have to assume mass distribution. We have to assume a mass density profile to perform these calculations, okay? You have let's say, two categories here. You can estimate the mass of individual cluster, and this you can do for massive clusters where you have a good signal-to-noise ratio. But usually this corresponds to few percent of your entire catalog. So to try to consider most of your objects, you are going to perform a mean cluster mass estimation, which is you have to stack the clusters. You are going, as Tom mentioned, you are going to select your clusters and divide them by richness, for example, and redshift bins. So you pick all those that are similar in these quantities, and you are going to stack to obtain a mean signal that is strong enough to obtain a mass estimate for given that richness and redshift bin, okay? But here, particularly, I will focus on a method to obtain individual cluster mass estimate, okay? So today we have both two presentations that described these quantities and show us nice plots. We have here our cluster, which is going to length the background galaxies, okay? So they are going to distort the shape of these background galaxies. And these formations that we want, okay? We are going to measure the reduced shear, so the ellipticities of the galaxies are correct, have to be correct by the point spread function, PSF, okay? And then have here the reduced shear. Beta is this ratio between the cosmological distance between lens and source, distance between the observer and source, and this is the distance between the observer up to infinity and lens to infinity. And these quantities here with this infinite here is due to photometric redshift uncertainty. People notice that it's better these quantities, when you consider this distance up to infinity, are better behaved than if you do not do like this. So this is due to photometric redshift uncertainty, okay? So the convergence and tangential shear are given by these expressions, where sigma is the surface mass density, okay? And this is the critical surface mass density, which is given by this ratio between cosmological distance, okay? The tangential shear is given by this difference between the average surface distance and the surface mass density, not distance. And they are given by these expressions. So you can note here where it enters the dependency on the mass density profile. Why you have to assume a mass density profile for your halo, your clusters, okay? So we are implementing the one methodology where you use I think the biggest difference from other approaches is that we use the full photometric redshift distribution of each background galaxy that was lengthed, that we have the information about the ellipticities, okay, to obtain the cluster mass estimate, okay. So here, this methodology, we obtain individual cluster mass estimation. We use the full photometric redshift distribution of each background length galaxy, okay. This method was used already in the weighting the giants analysis. And there, in this paper, they showed that this methodology provides almost unbiased cluster mass estimates in comparison with other approaches, okay? And one thing that I'd like to emphasize here is that in the analysis, to compute the surface mass density, they consider just this term, where you have to assume a mass density profile. In particular, they use INAF-OASBO, okay, where C, which is given, rho is the density is given by this relation. This is the critical density of the universe. C is the concentration parameter, and S is the scale radius. Okay. So this is the posterior we built. So this is the reduced shear that we have from each background galaxy, which was length. This is the theoretical reduced shear. This alpha here is a set of parameters which includes both the shear calibration and void profile parameters. Okay, this is specifically for within the giants. This void distribution. Okay, they use the step 1 and step 2 simulations. These simulations were carried out to fit the Subaru features, okay? So, for example, here, the idea is that we can apply this methodology in LSST. So we need to pick the LSST simulations to check what are given the LSST features of our survey. We have to check what are the features that we are going to obtain, what we expect when measuring the reduced shear, and which is the best distribution that will fit our results. So specifically for Subaru and within the giants, the void distribution was the best fit, okay? So you have this distribution in particular is a convolution of Gaussian Lorentz distribution. So we have here the standard deviation of the Gaussian distribution and also a gamma parameter for the Lorentz distribution that we are going to fit together, okay, in our analysis. But again, we have to check, given the LSST simulations, what is the best distribution which will fit the reduced shear that we expect, okay, in LSST. This term here is the redshift probability distribution of each background length galaxy, okay? And yeah, and another point here is that here this is the probability distribution of the reduced shear. But you also have to deal with the calibration of this quantity because you measure a reduced shear given your data and you have to calibrate this quantity. So there you have to add these. In general, for within the giants, it's just an additive calibration. You have to study it again. So the Weaklings working group, which are going to provide these kind of maps and information for the cluster working group, they have to deal with, okay, here you have the reduced shear information of each length galaxy. Or yeah, let's say here for our individual cluster mass estimation. And they have also to provide this calibration, okay? Because if they do not provide calibrated information, reduced shear, your results going to be completely unbiased, biased and will be wrong, okay? So, let's see, okay. So this is there is a collaborator in the cluster working group that performed different simulations. So we applied our methodology in this simulation. This is, okay, we have here 2.16 times 10 to 14 solar masses. And the true value was 2 times 10 to 14. So the methodology here is working pretty well for simulation. And this simulation is really simplified because all background galaxies are at the same redshift, at 1.5, and they have a perfect distribution. So, but okay, this is a first validation of our implementation, okay? And now we are applying it to Within the Giants catalog, okay? And we have to recover the shear calibration, specifically which one we have to use because they perform different analysis. So we are now trying to recover the Within the Giants results, okay? And let's see. Given this validation with the Within the Giants results, and you can ask why you are focusing on this particular survey, because one of the collaborators was the leader of this analysis, so it's easier to communicate and perform this kind of analysis, okay? But after that, the next steps, we have to include some improvements on this methodology. Because as I mentioned, the surface mass density is being computed considering just the simplest component factor, which deals with the density mass profile, okay? But we know that we have to include some corrections, like miscentering, as it was previously mentioned today. The observed system may be incorrectly centered, and this is affect your result. You don't identify the center of the cluster or the BCG cluster correctly, and this is reflect in your result, in your mass estimate. So you have to include this correction. You have to include also the two halo term, which is a correction to the halo profile for larger scales than pretty much than the virial mass, okay? And here this quantity will depend on the halo bias and the linear matter power spectrum also. We have the no-weak shear. When you perform this kind of analysis, you have to choose what is the radius, both looking outside the cluster, but inside the clusters. Okay, you cannot go too close to the center. Otherwise, you are going to enter in the strong lensing regime, and here we have to avoid it. Okay, we are performing an analysis just considering weak lensing information, so we have to avoid it, and we cannot enter. I think the next talk will let this clear. Okay, and so we have to correct. We have to include also this correction. And at last, we have the central point mass associated to the BCG, such that in the end, instead of computing the surface mass density, which affects directly the tangential and reduced shear measurements, we have to compute the surface mass density, the difference, like this, okay, including all these correction terms, okay? One thing that I don't know yet is something to study. If for LSST, what is the relevance of each term? I don't know yet, okay. Maybe, for example, maybe the no-weak regime, if we choose, let's say we are choosing good enough our radius, and this will not be relevant, but it's something that we have to study, okay? Mainly for in DS2, we expect to be able to do this already for DC2 simulations. We are talking and discuss because, as I mentioned, it's something that we need some results from the weak lensing working group, such that we can apply our methodology. We also need some response from the photometric redshift group. So it's something not so direct, okay? And another improvements that we want to do is to implement other meta density profiles, because INAF-OASBO, you are assuming that the halo mass distribution is spherical. So this, you are not taking into account substructures and anti-axiality, which are features that you expect in general for clusters. The good news is that for now we are just looking at massive clusters. So this is something that we expect it will be also a secondary correction, okay? All things that I described here, we are implementing the numerical cosmology library, which is a free software. The Sandro Vitente is going to talk about in details about this library on Thursday, okay? And we have on NumCosmo, we have not only the tools to compute cosmological quantities, but we have mathematical and pure statistical tools. So if you want to try, you have your code and you want to perform some statistical analysis, we can talk to us or Google it. And it's free to use, okay? We encourage you to do this, both if you want to contribute to the library. Everybody's welcome, okay? So conclusion, we have, as I mentioned, we have different uncertainty sources in cluster cosmology. And for now, the biggest problem is related with the cluster mass estimates, and you have to deal with this calibration of these quantities that we presented here. A new pseudo cluster counts likelihood that is a powerful tool to perform this kind of calibration in different situations that when you don't have the selection function of your catalog, for example, okay? And this is really important for the success of the cosmological analysis, okay? Here we presented individual cluster mass estimation tool that we are implementing and developing in order to apply in LSST, okay? And okay, we have the next step is to include finish the validation with the weight in the giants catalog, and then include the corrections that we need, okay? And that's it, and obtain the cluster mass estimates. I hope we can do it for DC2 simulations and then in real data, okay? One thing that I would like to emphasize in the end of my presentation is that cluster mass, we can look at it as a problem for cosmological analysis, but I would like to be more optimistic. It's an opportunity to understand the astrophysics of these objects. So I hope we can see these, all these tools, all things that we call that are cosmological frameworks and tools. Okay, math, you can see it as a problem, but if you open a little bit your eyes, okay, let's see it as an opportunity to understand more and more, even better, use these tools the other way, to understand the astrophysics of galaxy clusters, Weaklings, and all probes that you can use to connect with these objects and with the cluster mass estimation. Okay, thank you.
Is there any question?
So can you elaborate a little bit more on the selection function? So do you need a parametric model that you're marginalizing over? Or just how do you...
The selection function in the, okay. Here, here we, okay, I didn't mention that, I think. This F here is where we model our selection function. So we include some parameters. You can say if you have enough information, you can say if it evolves or not with Redshift, the completeness or purity. So you put it open and you model it in your likelihood, and then you fit yes, and you use it. These are free parameters that you are going to fit together with the mass observable relation or cosmological parameters all together.
So it still needs to have some sort of functional behavior. It can be a
but it can be as general as you want. You can just say, okay, I know that for magnitude lower than x, I don't expect to see any object. So it can be as simple as you want, or if you have more information, you can model it, improve. Okay.
I just comment on. I don't see also as a limitation in the sense, even if you claim you can assume like a non-parametric form, it's still dependent of the kernel or the basis.
Yeah.
And too much flexibility can allow you to have degenerated solutions. So as far as your parametric model is flexible enough or reasonable enough, that's fine.
Yeah. Yeah. And this is interesting because in this specific analysis that we performed, some of the parameters were completely degenerated. Because specifically we used just 21 clusters and we had 11 parameters to fit. So at first, okay, let's introduce this methodology, but we do not expect to have any important result from this. And it was a surprise that specifically the SS bias we could fit, and also the lensing bias were two parameters that we could have fit, even that the slope were completely degenerated. So this is interesting. Yeah.
Any other question? So I have a question, very naive. Can you repeat the physical meaning of the slope in the?
Okay. Here, if you already assume that the slope is equal to 1, you are just saying that the mass estimate that you are measuring from your observable, your mass prox, is directly related linearly with your halo true mass. And they will deviate from one another, from each other, just by a bias factor. So this slope means that you are allowing the form and a different from linear function between these quantities. Okay. For example, if you check the relation. A common relation that people use between richness and mass. You have the same kind of expression, and this tells you how this slope tells you if this relation is linear or not. Okay.
Okay, let's thank again Mariana.
Thank you.
The next speaker is Massimo.
computatore. Perfetto. Posso... Sì, attacco questa. Okay. Okay, so yeah, my name is Massimo Meneghetti. I work in Italy at the Observatory of Bologna. And my talk will be on strong lensing, so at least from what I understand from the program of the workshop, it will be the only talk focused on this particular regime of strong lensing. And in particular, I will talk about strong lensing by what I call substructures in galaxy clusters, and I will clarify in the talk what I mean by substructures. Okay, so I will report on some work that has been done, that has involved the work of many people that are listed here. We are a group based mainly in Italy, but with several external collaborators. And we just entered into the LSST collaboration through a group that is funded by INAF in Italy. So let's give a very brief introduction to strong lensing. So what is strong lensing? Strong lensing is a particular regime of gravitational lensing that we can observe whenever we have a very good alignment between the observer, mass distribution, which is big enough, the lens, and a background source that could be, for example, a galaxy or some point-like source like a quasar or whatever. So whenever there is this kind of alignment, if the mass of the lens is big enough, then we might have different light paths available for photons that are coming from the source reaching the observatory. And so we could see multiple images of the same galaxy in the background of the, or see simply large distortions, as it was pointed out in some talks today. So where can we observe this kind of events? We can observe them in the center, of course, of the lenses, because we require to have this kind of very, very tight alignment between observer lens and the source. And the lens can be a galaxy, and this is just a mosaic of lenses taken from the SLACS survey, where you see it's kind of red galaxies. They are early type galaxies, lensing some background galaxy, forming this kind of very nice arcs, rings, multiple images. And in this case, the scale of these events is of the order of 1 arcsecond or less. Okay, so we're probing scales that are very, very small near the center of the galaxies. Of course, then the biggest in the universe are galaxy clusters, and in galaxy clusters in fields like these two fields here, these are two clusters observed in the framework of the field Hubble 370 Max J0416. We have many features like this, large arcs here. Basically, as I will show you later, hundreds of multiple images of sources. Okay. In the background of these systems. In this case, we are probing scales that are of the order 1 arc minute around the cluster center. Okay, so as it was already mentioned yesterday during the wrap-up discussion, strong lensing is a very potentially powerful tool to investigate the inner structure of galaxies and clusters, and so to answer some questions that are related to how is on small scales. All right, so this kind of features that I just very briefly mentioned in the describing the slides, they can be used in a number of scientific applications. Okay, they can be used, for example, to probe the mass distribution of galaxies and clusters on small scales, as I was saying. Measuring properties of the dark matter halos, like their shape or their density profile, or the content of substructure. Okay, this is particularly relevant if you wants to study the nature of dark matter. Okay, but then we can also use these strong lensing events to do cosmology. Okay, so to do lensing cosmography, measure time delays, and then derive estimates for H0 and other cosmological parameters, do R statistics and so ever. And then we can also use the lenses as powerful natural telescopes to investigate the high redshift universe, so study the structure of the sources rather than of the lenses, and answer some other cosmological questions that are related, for example, to how the process of reionization took place at a redshift. And right now, basically just scratched the surface of what we can learn from strong lensing. Right now, what we can do with strong lensing is limited as to a few hundreds of lenses, both galaxy scales and on cluster scales. But what's ahead of us is something that we can't, it's hard even to imagine right now for people working in this field, because we are going to, with instruments like LSST or Euclid, we're going to make a kind of quantum leap and gain in terms of numbers of available lenses, orders of magnitude. Okay, so with Euclid in particular, we expect to observe, to detect of order 200,000 galaxy scale lenses and of the order of a few thousands cluster scale lenses. Okay, and the combination of these two instruments would be really a great thing to put in place, right? Because combining the kind of color information, the cadence that LSST and the depth that LSST can provide with the spatial resolution, infrared photometry, and whatever that Euclid can provide would be really a great benefit for exploiting the science that could be possible to exploit with these huge data sets. All right, but coming back to these days, as I said, the focus of this talk will be on strong lensing by clusters. And these last years, there have been a kind of golden age for strong lensing by clusters, in the sense that we have had access to data that were of a precedented quality, thanks to the effort of the HST that was used in a couple of, actually more than a couple of surveys targeting the course of a few galaxy clusters. Clash was already mentioned in the previous talk. Then we have had the frontier fields that have dedicated more than 800 orbits of HST to observe at the depth of the Hubble deep fields, essentially the course of 6 galaxy clusters. These are the kind of limiting magnitudes that you can reach within these fields, and without accounting for the fact that there is magnification also. So it means that we are also we're able to gain further depth because of the magnification provided by these huge guys that were targeted in these surveys. So our group has worked on this data set, okay, and we have discovered a few interesting things that I'm going to share with you now. So within these fields, as at the depth that can be reached in these fields, there are basically, as anticipated, several hundreds of families of multiple images that are hidden behind these clusters. Okay, so each of these families of multiple images, they provide you a measurement of the deflection field that is basically produced by the mass distribution of the cluster. So you can use this kind of information, all these multiple images of background sources, in order to build models of the mass distribution of the clusters. And with this observation, we can do this kind of work with incredible level of detail and robustness. And you can probe at the same, in lenses that are so big, you can probe both the large component, the large scale component of the clusters, and with this I mean basically the smooth halos of dark matter that we believe they are located around the brightest central galaxies of the cluster. But we can also, as you can see here, okay, which is a zoom of this region of the cluster, we can probe even smaller scales. Okay, so here we have inside this cluster we have a lot of galaxies that we could assume they traced the substructure in these clusters, and these are all potential lenses. As indeed inside these fields that have been targeted by the frontier fields, we have discovered many of these small scale lenses, these galaxy strong lensing events that can be used then to measure essentially the mass content around the galaxy. So this is what I mean by substructural lensing in the context of this talk. Okay, and I will show that studying what we have learned from these models that we can build using these constraints is quite interesting, because we are aligning a kind of tension between what we observe and what we typically see in numerical simulation, state-of-the-art numerical simulation. So I hope to trigger some discussion about this later. All right, so the constraints that I just showed in this image here, they're not sufficient in order to provide to build a very robust mass model of the clusters like this one. Essentially because lensing is a geometrical effect. So in order to decipher these lensing effects that we are seeing in terms of splitting of multiple images, we need to associate the distance to the source that is being lensed by these monsters. And so we need to access this information through spectroscopy. So apart from the HST observations of these clusters, what we are using is also state-of-the-art spectroscopic observations of these clusters. And in parallel to CLASH, we have run this project, the CLASH VLT project, that have provided spectra for hundreds to thousands of cluster members inside some of the CLASH clusters. There are data provided by this other HST program, GLASS, PI'd by Tommaso Treu, and there are several ongoing and the past programs that have been using the MUSE integral field spectrograph to target these clusters. And MUSE is really an amazing instrument for this kind of science, because MUSE basically has a field of view which is exactly the right size that we need to capture the strong lensing region around the core of a cluster. So the field of view is one arcmeter inside. Okay, so in this case with a couple of MUSE pointings, we could basically image the whole strong lensing region of a cluster like 0416, and basically each pixel in this patch here is a spectrum that you can extract from a data cube, and giving you access basically to all the information you need to measure the redshifts of the sources, and also to measure the membership of the cluster galaxies that we need in order to build a reliable model. Okay, so with this kind of observations, we can map the mass distribution which is in front, inside, and outside of the background of these clusters, allowing us to take into account all the possible contributions to the lensing signal, okay, if we want. And MUSE also is a very powerful instrument to find strongly lensed galaxies, because you basically see emission lines that pop up in the frame, in the cube, in the Muse cube at a single frequency. So you basically, if you select that particular frequency, you only see these multiple images of a single source, and you don't see anything. So it's very easy to identify the multiple images in this way and to make the right associations between the multiple images. All right, so what is the strategy that we used in order to build a mass model using this kind of ingredients that I just said? So positions of multiple images and their reshifts. The technique that we used is often referred to as a parametric method to build a mass model. What does it mean, a parametric method? It means that we use the light emitted by the galaxies in this cluster in order to have a guidance of where to put mass, okay? And we place some large-scale halos centered around the brightest central galaxies of the cluster, plus we attach dark matter halos to each other galaxy that we see in this field of view, okay, and then that we know to belong to the cluster, okay. So each of these mass components is somehow parameterized with a density profile, with a shape, with a position. So these are the parameters that we try to change to vary in order to fit all the lensing constraints that I showed you before. Of course, this kind of process can involve a very large number of parameters, so usually use tricks in order to limit the number of parameters. One trick that we used, for example, to include the population of the cluster galaxies into the model is to treat them as using some scaling relations. So we try to assign to these substructures, what we call substructures, a mass which is related to the luminosity of the galaxy that we identify in the cluster through this kind of relations here, okay? And this, of course, reduces the number of parameters that you have to fit, because in order to describe the whole cluster member population, you just need 3 or 4 parameters. That's it. All right, so what have we learned from this kind of work? As I said, this talk is focused on what we have learned by looking at the small scale structure of these clusters. And on a small scales inside this cluster, we found some puzzling results. Already when we tried to compare the outcome of our models to the subhalo mass function of we could extract from state-of-the-art high-resolution hydrodynamical simulations of galaxy clusters. Okay, so here I want to report the results of a couple of papers where we have noted that there might be a problem with the shape of the mass function that we measure compared to what we typically find in simulations, in the sense that there might be an excess of massive subhalos in the cluster that we have reconstructed compared to what we see in simulations, what is predicted by theory. And also there might be an excess of subhalos that are, again, massive subhalos near the center of the cluster, which is completely missing in the numerical simulations, as you can see here in this plot here. Okay, so how do we explain this kind of differences? That's an open question. First of all, we want to be sure that there is such a discrepancy. So what I'm going to show you is what we have obtained by using even a different approach to try to identify this problem, which is based on the signal that the substructures that we see also in this model here produce in terms of strong lensing. Okay, as I already mentioned before, we see several cases of galaxy strong lensing events in these clusters. We want to see if with the statistics of these of galaxy strong lensing events, we can learn about something about the small scale structure inside these clusters. All right, so to explain the method that we have employed, we will use this kind of animation. So this is a model of MaxJ0416 that we have obtained from the data set that I showed you earlier. Okay, so once we have the model, so a guess of how the mass distribution is inside this cluster, then we can look at what happened to the sky, which is behind this cluster. So we can de-lens basically the whole sky behind this cluster. So suppose that we are looking through this lens, through these 2 pointings of our telescope. What is the region of the sky that we are accessing through the lens? We can discover that if we de-lens the sky, as I was saying. Okay, so if we go back to high redshift, okay, we discovered that the basis of the model that we have built, the sky that we are looking at is something like this. Okay, so what we have seen is that basically in the background of the lens is like if the sky is folding up, okay, and it's also squeezed along some lines that are these dark lines here. So in the gravitational lensing terminology, these lines that you see here in dark color, they are called the caustics of the lens. Okay, so these are very highly magnified the regions on the source plane where you have extreme magnification. Okay, indeed, the sky there is really compressed and squeezed along these lines, and we can extract these lines. Okay, so the contours, and we can now do the reverse operation. So from the source plane, we can go back to the lens plane using the model of the lens that I showed you earlier. Okay, and here I want you to focus your attention on these 2 blue circles here, but also to what is happening around this very small caustic here. As you can see in this plot, we can clearly identify a very long caustic, which is the caustic of the cluster produced by the large scale component of the cluster. But there are a lot of other caustics that are that we call secondary caustics, and that I will show you now. They are connected to the smaller lenses that we have in this density field. Okay, so let's see what happens when we unfold the sky. We go back to the source plane. Okay, what happens is this. So you see the splitting of multiple images of one source into multiple images to form these large tangential arcs or these radial features here. So we understand now how this kind of arcs or these kind of arcs are forming. Okay, but if you looked at what was happening around the secondary caustic I pointed you to, then you see that essentially around that line that is produced out of the unfolding of the sky, these are the critical lines of the cluster. Okay, so it's the same lines but on the image plane rather than on the source plane. So there we have the formation of this galaxy scale strong lensing system. Okay, so essentially now what we have discovered is that all these small critical lines that are produced by the secondary caustics that I was showing you in the beginning of the movie. So essentially these caustics here, these are all critical lines that surround cluster galaxies, and the presence of these secondary critical lines means that we might each of these galaxies could potentially produce a lensing event if there is a source which is located at the right position inside the corresponding caustic on the source plane. And the caustic is a small caustic like this one, which is what we could see at the beginning of the movie. Okay, so in other words, these kind of events here They appear because in the cluster there are a lot of secondary caustics like this one, and they occur, these kind of events, if you have a source that falls inside one of these caustics, okay? So this plot here shows you what you get when you try to plot the critical lines of a real cluster, as they are derived from the strong lensing models, okay? In this case, this is max J 1206, and the critical lines of a cluster of about the same mass taken from a numerical simulation, okay? So as you can see, the large scale critical line of this lens here is very similar to the large scale critical line of this guy here, but there is a lot of a signal that we can see on small scales simply by looking at the presence of these secondary critical lines that we don't see in this cluster. What does it mean? It means that a cluster like this one is not capable of producing the strong lensing events that we see on small scales produced by a real cluster like this one. Okay, simply because there are no critical lines, there are no corresponding caustics within which we could place a source in order to see it as a galaxy strong lensing event. Okay, so we have performed this kind of comparison that I just showed you in a more quantitative way, focusing on the 6 frontier fields and on this other cluster, max J 1206, which is a cluster for which we have we know that we have been able to build a very robust mass model using the strong lensing constraints that we found in the clash data, and spectroscopic data taken from a few programs with observing programs with MUSE. And the way we have quantified essentially the ability of these clusters to produce galaxy strong lensing events is by means of measuring their strong lensing cross-section. The strong lensing cross-section is the area on the source plane within which we could place a source in order to see it lensed as a strong lensing event. Okay, so for what I've told you, I showed you earlier, what defines the size of the cross section is the size of these secondary caustics that we have inferred from the lens model. Okay, so if we sum up all the areas of these secondary caustics here, we end up defining a cross section, okay, for strong lensing by galaxies in the clusters. And if we divide the cross section by the field of view within which we are looking at through the lens, then we define the probability that a source on the source plane is being lensed as a set of multiple images. Okay, so as a strong lensing event. So if we do this kind of job, and we measure then the probability for this kind of events in the 6 frontier fields and in max J 1206, what we get is this kind of a function. This is the probability as a function of the redshift of the sources, okay? And this tells you very little because you usually think in terms of number of strong lensing events, right? So we can transform this probability here into a number of strong lensing events if we just multiply this probability by a number density of sources. So if we take this number density from a deep field, like for example the Hubble Ultra Deep Field, what we get is this kind of expectation for the number of galaxy strong lensing events that we could observe as a function of a limiting surface brightness of our observation. So as you can see, in the case, for example, of this cluster 1206, we expect up to 3 galaxy strong lensing events only in this cluster. Okay, and we have similar numbers for the other frontier fields. So the first question to answer is, do we find this number of galaxy strong lensing events in this cluster? And the answer is yes. So in the clash data, we can identify these two events, for example. These are two sources at redshift 3.75 and 1.42 that are lensed by two cluster members, one to form this kind of triplet of multiple images. In this case, we have a complete Einstein ring, okay? And these are the critical lines, secondary critical lines around these galaxy scale systems. If you look into the Muse data cube, around this other cluster member, there is a signal. You can see a signal, 4 peaks of emission at the wavelength of the Lyman alpha line, okay? So these are 4 images of a Lyman alpha emitter, which is at redshift 5 behind this galaxy, okay? So we see quite a significant number of events. So if you think this is a field of view of a few arc minutes, typically in the field, we expect to see maybe 0.5 galaxy strong lensing events per square degree. Here we are seeing an higher rate by a couple of orders of magnitude at least. Okay. All right. So what happens if we compare this probability for galaxy strong lensing events to what we see in numerical simulations? I showed you already visually that there is some tension. Now we can apply exactly the same method to measure the probability, both on the data and on the simulations. And you see here is a plot showing the difference. So again, here these are frontier fields, max 1206. The red line here shows you what kind of probability you measure when you analyze high resolution hydrodynamical simulations with all by state of the art, I mean with all the current implementation of the baryonic physics included, okay? All right, so this is a comparison based on a set of 29 massive clusters. Each of them has been studied using a ray tracing technique. And we have basically combined to build this plot all the snapshots for these 29. Yes?
Just for clarification, this looks like the inverse of the missing satellites problem on larger scales.
Exactly. That's the interesting point. It is in my conclusion, indeed. So, yeah. It is. It could be very, yeah.
Sorry. These simulations you're showing there, is this papers, Planell's? Which paper is the simulations?
So it is a set of the techniques that are used to simulate this cluster. They are described in this paper by Planell's et al. 2015. Okay. But then there have been some new versions of simulations done by the same group, and they are described in these other follow-up papers.
Because I have a paper that we conducted this work on AGN simulations, and we get much higher numbers. We get around 300 per million.
Sorry, I didn't understand.
we did a paper on this, and we get probabilities which are closer to 300 parts per million, which is much closer to your result, not 10s and 20s. And that's why that's a comment. And the second point is, in order to do this kind of comparison, you have to somehow treat how representative is the field you're looking at, right? How do you do this? How do you treat for this selection biases that you have?
We basically took the most massive clusters in the simulation, and they have about the right mass to be compared with the frontier fields that we have, and max 1206. The cluster that we have used for this comparison. We didn't attempt to select these clusters in terms of their strong lensing signal, although we did some tests with the MOCA code by Carlo Giocoli. I think you're familiar with that, to try to figure out if there are problems related to the selection of these clusters. And we didn't find a way to match the expectation from the simulations with what we measure observationally. So with regards to the comment that you were making about the results you got from AGN simulations, the only way we can bring this curve close to the observational results is by switching off the AGN feedback in our simulations. In this way, if we basically enhance the concentration of the subhalos by means of overcooling of the gas and star formation, and then we can these curves closer to what we measure. But with AGN, so we did several tests, and this is the result that has been fine. Yeah, yeah, I'll be very interested to hear from you. All right. So as I said, we did several tests. So here I mentioned just a few of them. One is using MOCA, which is for those of you that are not familiar with that. So is a code to create mass distributions of cluster scale lenses completely analytically. Okay, so we were worried in the beginning that the results that we were finding by doing this kind of comparison, they were somehow biased by the spatial resolution of the simulations. So using this code, we basically avoid to have any limit in resolution. We can ideally go to infinite resolution. But still, as you can see here, we still find there's a huge difference between the lensing signal that we measure in the simulations and what you get in the observation. So these simulations here, they're of course based on the same ingredients that we measure in the numerical simulation. So the mass function is that of the numerical simulations. The spatial distribution of the subhalo is that they can measure in the numerical simulations and so forth. And as I was anticipating, if we switch off the feedback from AGN, then we get closer to the results. So this is the test that we did to understand how important are the effects of variance on these results. We also tested. We did other tests to measure, to assess what is the importance of mass resolution, and or if the mass resolution that we have is sufficient, essentially. And we did also some tests to include the structures along the line of sight to see if they were able to increase the signal from the cluster galaxies, but we didn't. We weren't able to solve this discrepancy yet. Of course, we could have problems in the mass models, right? So our lens models could be somehow incorrect. So we did a lot of testing also to assess this kind of possibility. We ran a challenge that involved basically participation of the whole community of people working on strong lensing modeling on cluster scales, where we simulated images like this one of clusters observed with Hubble Space Telescope. We distributed to these groups the typical data sets that they commonly use to reconstruct a cluster, and return the model of the cluster compared with the input. And in this case, for what regards to the signal produced by the cluster galaxies, what we could see is that we can recover the mass around each individual cluster galaxy with the methods that I illustrated earlier, with a precision which is of the order of 20%. Okay. Then we can do some other tests. For example, using the spectroscopic measurements that we can make using the Muse data set. Okay, we can measure the velocity dispersion profile around the brightest galaxies that are in these clusters, and see if the velocity dispersion that we measure is compatible with the velocity dispersion which is predicted by the lens model. And as you can see from this plot here, these are measurements of the velocity dispersion around this cluster member. This is what the lens model would predict. So we are in very good agreement in this case. And then there are other tests that was possible to do to assess the robustness of the lens models. One was offered by this observation of this quite famous strong lens event in the cluster MAX 1149, and suppose that everyone heard about these lensed supernovae that was observed into this set of 4 multiple images around this cluster galaxy in this cluster. So this is an event of galaxy-galaxy strong lensing of the kind that I was discussing in this talk. Okay, and you see this galaxy here, this part of this blue galaxy that is lensed by this cluster member here, is essentially one image of a galaxy which is multiply imaged by the large scale structure of this cluster. So this image that you see here, okay, and these other galaxies that you see here, they are all multiple images of the same galaxy. And one of these images happens to be overlapped with this cluster member. So inside this image here, we see a galaxy supernova, strong lensing event. Okay, so this case here is particularly unique because this is a variable source. Okay, and since the gravitational lensing effect implies that there is simply because of the different path that the light travels to reach the observer through 3 different lines of sight, it induces some time delay between the images, right? The source is a variable source. Then you have the chance to measure the time delay between the images. The time delay is another probe of the gravitational potential of the lens. Okay, and so this is what it was possible to do in this particular system here. So, having observed this system here in November 2014, building a mass model for this cluster, several groups they could anticipate the reappearance of the same supernova, exploding in another multiple image of the same galaxy. Okay, so the model tells you that basically in this galaxy, in this image here, the supernova appeared already 16 years ago. Okay, but it was expected to reappear in this other image near the center of the cluster 1 year after the discovery of this set of multiple images. So we could basically test the lens models to see if they were able to predict the reappearance of this supernova in this other image. And this is what has been done, again involving basically all the groups that were working on the frontier fields. The supernova has reappeared in this position here, you can see, in December 2015. Okay, so from the light curve of this image here, the lens model could be used to predict the light curve of the supernova that was supposed to reappear at this position. And so it was possible to predict with the model not only the time of the reappearance, but also the luminosity of the image that was going to reappear, and also the time delay, of course, of the reappearance. Okay, so 3 strong lensing observables that are tracing 3 different derivatives of the lensing potential. So time delay measures the lensing potential. The deflection angle, so the image position, measures the first derivative of the gravitational potential, and the luminosity, so the magnification of the supernova, measures the second derivative of the lensing potential. And this is how the experiment worked. Okay. This is where the supernova reappeared. This is the predicted position for the reappearance of the supernova. This is the magnification predicted by our lens model, and this is basically where the magnification of that has been measured on the reappeared image. And if you read this plot along this axis here, you see essentially what is the predicted time delay, okay, which was also predicted correctly. Okay, so this is of course a unique way to test the models and to show that they are very, very robust and successful. So, yeah, come to the last slide. What we have seen by building these what we think are very robust and reliable models of these clusters, observed in the framework of the Clash and the Frontier Fields initiatives, is that there is a quite high rate of galaxy-galaxy strong lensing events in this cluster that we can use to probe the small-scale structure of these systems. We have compared these observed systems to what we expect from numerical simulations, finding that there is a strong tension between the probability to observe this kind of events in numerical simulations and in the observations. So we are now trying to find an explanation for this discrepancy. Okay, maybe there is a fundamental problem with lambda CDM, which could be the most exciting discovery, of course, but as you pointed out already, it goes exactly in the opposite direction to what were the previous claims. So observationally, we always believe that we see less substructures, for example, in the local group compared to what is predicted theoretically. Here we're finding the opposite thing. Okay. Or perhaps we are highlighting some limitations of the numerical simulations of small scales. Okay, there are some papers that appeared in the last years, in particular by Frank van der Bosch and in this group, that are claiming that there is a fundamental limit in the simulations. So there is still a lot of numerical effects that basically destroy the small-scale structures in the dark matter halos, okay, and these kind of numerical problems, they are related to non-optimal softening and discreteness noise. Okay, if this is the case, this is a problem that it doesn't only affect what we can learn about the substructures in clusters, but it scales down also to galaxy-scale systems. So there is a huge effort going on right now to try to understand if warm dark matter, for example, is an alternative to cold dark matter that rely on what kind of subhalo mass function we can measure observationally and compare to simulations in order to find an answer to this kind of question. So if this is the case, if this is what we are looking at, that's a big problem also for this kind of science. Okay. All right.
So there is time for a question.
I suppose the folding simulations you have shown from higher redshifts are in a Komov frame, right? It's normalized by the scaling factor.
Yeah. So
does it reasonable? You know, because you are showing space-time folding.
Yeah. Well,
it's not common.
So, actually, what I was showing was it as a function of redshift, not of time. Is that the question you were asking?
Does it in a Komov frame? You mean you do the simulation divided by the scaling factor? When you do the numerical simulations from high redshifts, you are just in a Komov frame, right? You don't see space-time.
You mean the hydrodynamical simulations?
Yes.
Yeah, of course.
Okay, I'm not sure if it's reasonable, you know, because you don't see space-time folding in a Komov frame.
So, but what I was showing is also the numerical simulation is used only to.
This is like a Channerin Zeldovich pancake, like what we are simulating, right?
Yeah. No, but the numerical simulation is only used to use a distribution. Okay, then the ray tracing simulation is just using this kind of information. So we just transform the mass distribution of the lens on a single plane into a deflection angle field. And then the deflection angle field is what I used to delens the background sky.
I see.
Okay.
Yeah, okay. Maybe that's one source of the bias you are observing, okay, between the simulations and the real data. Just to think about.
Actually, we run out of time. So, yes, there is going to be discussion at the wrap up, 4:30. So let's meet again at 4. Now there is coffee break with the talk of Jorge. So let's thank again Massimo. Amazing.
Strano.
No, infatti, cioè, affascinato. E mi sono rimasto, non ho più guardato l'ora perché stavo proprio... Cioè, sta cosa della supernova è... Ah, quello sì, è stata...
Can these events be considered as a compound?